We have talked about clustering in a general context. The idea that you try to find natural groupings that would occur within your data, and perhaps the most or the next logical step is to think or come up with something like k-means. The idea that if you're close, you're likely to be similar, and if you're far apart from one another, you're likely to be dissimilar. This only works well if you don't have that many dimensions, that many features to look at. It also only really makes sense if you scale the data so that every feature is on the same, or at least in comparable scales in terms of the distances between observations. And there's many ways to scale a data set, but that's at least doable. And if you have categorical and numerical values, then you need to pick corresponding, or at least metrics or distances that have the same types of properties. You know, one for the numerical half of your data set, one for the categorical half, and then you find ways to join these things together to create a hybrid distance. But you try to avoid as much as possible using distances that have completely different properties, right? If you do have categorical variables, you don't have that many options open to you for distances. If you have numerical variables, you do have a fair number of options, at least infinitely many options, because you can use all of the p distances, right? And so there's like an embarrassment of riches. A few other things to keep in mind. Validating the results of your clustering is actually quite difficult, right? And we've mentioned that you might use external information to try to validate the results, but it's quite conceivable that the external information you have is not aligned with the natural groups, in which case, well, this isn't going to really be helpful for you to validate results. The solution is that you run more than one clustering scheme on the data. You run multiple schemes, either with algorithms such as k-means with different starting conditions to see if you're going to be seeing a lot of difference with, you know, to see how robust the clusters are, or if they're really dependent on the initial starting conditions. That's one thing of interest. The other thing that you want to do is, like, you know, with something like k-means, it's not obvious what the k-value should be at first, and so you'll want to run k-means with a variety of k's to see if there's some way to validate using relative schemes which value of k is best or better given the data that you have and the distance metric that you've selected. So that's another main takeaway. You should never just create one clustering scheme, right? It's the results of multiple runs that is of interest to you. You compare runs with one another. Okay, so now I'd like to talk to you about two additional types of clustering algorithms. We'll speak about hierarchical clustering and about spectral clustering. Hierarchical is fairly straightforward. It's easy to explain, it's easy to see. Spectral clustering, that's a sophisticated one. It's mathematically heavy. I'm not going to talk too much about the mathematics behind it, but I do want you to see or realize that some of the algorithms are somewhat counterintuitive. They still achieve things that we want them to achieve, which is to say, find observations that have something similar and group them together. But it might do so in ways that this isn't how we think our brains actually work or do things. So there's a spectrum, if you want, of complexity of algorithms, some of which are quite natural, quite intuitive, like k-means and hierarchical clustering, and then it runs the gamut, and eventually we'll see things, or we won't see things, but we could talk about latent Dirichlet allocation or expectation maximization or spectral clustering, and it's not obvious at all why this should work. I mean, mathematically, if you dig down, you'll see why it will work, but it requires a fair amount of sophistication. So the idea there is to show you that, it's not just always going to be easy ones. You can do harder ones as well, or more sophisticated ones. And finally, we'll talk more about how we validate the results of clusters. I will release, not quite right now because I'm not done cleaning up some of the notebooks, but I will release some R code that shows you how you would run some of the more complex algorithms. So, I mean, in order to run spectral clustering, you don't really need to understand the mathematics behind it. But I find it damaging if we just give people the algorithm and say run with it. So we'll talk about these things. I'll give you some examples of how you would run these things in R in notebooks, and then afterwards we can discuss whether there's any of these would be appropriate for your specific problem, and if they are appropriate, how do we need to tweak them to take into account the nature of your specific data and what it is that you ultimately want to do with the clusters that you have found. All right, let's start with hierarchical clustering. You've seen examples of hierarchical clustering before. I don't know if you recognize this diagram. Perhaps we're not used to seeing it wrapped into a circle, but this is the tree of life. This is how species are regarded as similar or dissimilar based on their, why would you call that in English? The genome? The genome, like the collection of their genes and DNAs and what have you. And that's an interesting thing, right? I mean, if you think of the orders of life, like mammals and reptiles, and I don't actually know all of the different orders, but it's actually pretty difficult to find them. Like Linnaeus, way back when people started thinking about this, had like rules. And you know, what is a mammal? Well, typically we'd think of mammals as something that might have fur, or potentially that lactate, or that, you know, do live births. Hot-blooded, warm-blooded mammals, that, you know, roughly speaking, that's what we think of when we think of a mammal. Because, you know, it's basically a description of what humans are and what primates and apes and other types of close neighbors are. But there are mammals that do not lactate. There are mammals that don't give live birth. It's actually not a 100% clear-cut definition. Same thing when we talk about like plants and fungi. There's going to be some sort of, or fungi, I don't know how to pronounce that word to be honest, but there's going to be some sort of overlap. Whenever we give description of an order of life, we are basically labeling a cluster of observations that are close to one another, a cluster of species that are close to one another. And, well, amongst that cluster of species, for instance, human beings, or humans, Homo sapiens, we have these qualities, so that's how we describe our cluster of mammals. And we could go, you know, further down to primates and what have you. But these are not hard-coded, hardly delimited groups. Right? They are similar, they're close to one another, we place them in the same cluster, we give it a name, we try to give it a description, but the borders are fuzzy. And that's an important thing to keep in mind. So this tree here, this tree of life, is an example of hierarchical clustering, where all of the species with their genomes, or at least with a number of genetic characteristics, have been compared. And the ones that are very close together, and ones that have basically the same genomes, are considered to be part of the same family. But you can imagine a setup where somebody here, a species here, you know, has the same or close to the same genome as the species next to it, and there's a chain of species, like one by one, the genomes are pretty close, but you get to the end here, and this species, whatever it would be, while being in the same cluster as this species, is actually fairly distant from the cluster, from the species, and it's a bit of a mess. It's a bit confusing. It's not obvious. We don't typically deal with very sharply defined clusters in the real world. So hierarchical clustering is one of the ways in which you cluster your observations, and you cluster them into a hierarchy of clusters. So what that means is that the order relation is set containment. So you're below, cluster A is below cluster B in the hierarchy if cluster A is a subset of cluster B. This is what it means. So there's two main strategies. You might do a bottom-up hierarchical clustering. The way this works is every single observation at the very start is considered to be part of its own separate cluster. So if you have n observations, you have n clusters to start with. And then you merge them. You will look at all of the pairwise distances or pairwise similarities. So if you have n objects, you're going to look at n times n plus 1 divided by 2 pairs. And you'll compute a measure for each of those. And the two observations that have the greatest similarity or the smallest distance, depending on how you measure these things, get merged together into one cluster. So we've moved up one level. This is the first real step. And instead of having n clusters, we now have n minus 1 clusters, right? So we have n minus 2 clusters that have only one observation, and there's this new cluster now which contains the two observations that were closest together. At the next step, now you have n minus 1 clusters, and you're going to compute the distance or the similarity between the various clusters. You don't have n clusters anymore, you have n minus 1. But as it happens, a lot of these comparisons have already been made. Like, let's say cluster 1 and cluster 2 each contain only one observation. There's no need to recompute their distance at the next step because you've already done that at the bottom step when you were computing the distance or the similarity between all of the observations. So at the second step, you're going to compute the distance between the clusters and the observations. Well, they're all clusters really, and then you'll merge them together again according to which two clusters are closest together. It could be that this time around two other observations, two clusters are meant to be closest, so they get merged, and now you would have two clusters of two observations and n minus 4 clusters of only one observation. But it could also be that that cluster of two observations that we created from the first step is actually closest to a cluster with a single observation at that step, and that gets merged into a cluster with 3 observations. Either way, you've gone up one level and you have not as many clusters as you had before. And then you'll go through this process until every single cluster has been merged. All the observations are now in one cluster. And the topology of this hierarchy, of this tree, is what gives us the hierarchical clustering structure for the dataset. The big challenge there is how do we decide how to measure the distance between clusters. It's easy to measure the distance and similarity between observations, but if I have a cluster of 5 observations here and a cluster of 7 observations here, what is the distance between the clusters? What does that mean? Now we call this the linkage strategy. The way in which we compute the distance between the clusters is the link between the clusters. And just as when we do k-means, we need to specify a distance metric and a parameter k, well, in hierarchical clustering, you don't need to specify the number of the number of clusters you want to find. You don't need to specify a k, but you had to specify something in k-means. In hierarchical clustering, what you need to specify is the distance. Again, you can't get away from that. And the linkage strategy, how you are going to be combining these things. So you've removed the need to specify the number of clusters up front, but you've added the need to specify how clusters get merged together. And this game of cat and mouse, basically, this arms race, it's literally across the board. Every time you come up with a new strategy to try to reduce or remove one of the complications from the previous cluster strategy you used, Well, there's a new thing you need to come up with. You can't seem to get away from this. You'll need to make one or two fairly arbitrary choices whenever you run any clustering algorithm. We'll talk about the linkage strategies here in a while. So that's the bottom-up approach. We call this the agglomerative approach. We build, or we agglomerate the observations into a successive series of clusters until there's all of them are in one cluster. But there's also the top-down approach. You start with all of the observations in one cluster, and then you look at various splitting of this cluster. And you will pick the splitting which is somehow optimal. And so you might start with like, you know, your n observations in one cluster, and then you find that there's a splitting which would be best, and so you end up with a cluster of, I don't know, I'm guessing, I'm throwing numbers, n minus 3 observations and 3 observations. And then you keep on splitting these clusters until you get to the bottom, and every single observation is considered to be in its own cluster. It's the same sort of approach, except you start with all of the observations in one and you go down. As it happens, bottom-up agglomerative is substantially faster than top-down divisive. Bottom-up is of order n squared, basically, or n if you want. You only have to compute pairwise distances, and you move up, and as you move up you have fewer and fewer distances to compute. But top-up, when you're looking at the ways in which you can split all of the observations into 2 clusters, that's an exponential thing. You have 2 to the n choices, and if n is very large, top down is not a good choice. Bottom up is a better choice. And the nice thing about this is that you don't typically have to grow the tree all the way up to the top. Because, you know, you might say, well, I'm interested in finding clusters. If I go all the way up to the top, all I have is everything is in one cluster. So you'll stop growing the process at some point once you've reached a number of clusters you feel comfortable with. Right? So you don't have to do all of the computations that way. I'll show you some charts here, perhaps that will make this a little bit easier. Think of it this way. Let's say you had 5 observations, A, B, C, D, E, and you want to cluster them together, or at least find the structure of clustering. So you will start by computing the difference or the distance or the similarity between all the pairs, and perhaps it turns out that A and B are closest together. They're the ones that are most similar. So at your first step, you had 5 clusters, each of which had 1 observation in it. The next step, you have 4 clusters, the clusters C, D, E, which each have exactly one observation in them, and the cluster AB, which has 2. The next time around, like, you know, what is closest? Well, it might turn out that D and E are closest, so you join them together. And then D and E might be closest to the value C, so they get joined together. And at the end, you can actually join C, D, E, and A, B together because there's no other choice. And this sort of tree structure here tells you what the clustering structure of the data set is. If you decide that you want 2 clusters in your data set, you don't really have a choice. You're going to have to sort of slice it right up here and shake it loose, and you will see CDE come out and AB come out. Okay. The main question in hierarchical clustering is, how do you decide how to split or how to merge the clusters? So this is this idea of linkage that comes up here. Another issue, at what level do you cut the tree? At what level do you stop growing it's actually called a dendrogram, not a tree, but at what level do you stop growing that dendrogram? When do you say, I'm cutting it here, and whatever comes out, these are my clusters? That's actually a difficult question to answer. It's another arbitrary question, right? You have to select a level at which you cut. There's a lot of issues with clustering with hierarchical clustering as a strategy. It is probably a better idea to use latent class analysis. So this is a strategy which is somewhat like hierarchical clustering, but that overcomes some of the issues. But it's a purely statistical method, And I think it's easier for me to talk about hierarchical clustering. If you're interested, then you can take a look at latent class analysis later as well, because there's a lot of interesting things we can learn about clustering in general by studying hierarchical clustering. This perhaps would look a little bit more like the kind of result you might expect to see. Like, imagine you have, I don't know, how many observations do we have in total here? I see 50, that's probably 50 observations. And each of the observations has 3 measurements. A measurement in pink, a measurement in, what color is this? Can I say orange? I'll say orange. And a measurement in yellow. Well, you could also argue that they have a measurement in white, which is the distance from the top of their measurement all the way up to 3. But for the time being, let's just forget about the white. So you represent the observations as being a combination of pink, orange, and yellow. And the size of each of these things tells you the importance of each of the features of each of the components. Now, in this tree, you have 50 different observations. You're going to try to find the 2 observations that are nearest one another, in terms of like that are the most similar. And if you look at them, basically you're looking for the first branching point, or the lowest branching point. And it looks to me as though 13 and 34 are probably the closest ones. It's the smallest or the earliest branching. So amongst all of the observations, 13 and 34 were found to be most similar. So they were joined into a cluster right here. Then the next branching point seems to be, what do I see here? Perhaps 1 and 12, or perhaps 14, 37. Not super clear, but you know, that 1437 looks like it could be the next. So yes, again, very similar to one another. Not quite as similar as 13 and 34 according to whatever measure of similarity we used for this to produce this chart, but the next similar, the next most similar up. And you go through all of these things and you start joining clusters together. Like at some point, 13 and 34 as observations are going to be considered to be pretty close to observation 40, and they will be joined together here in a cluster, in the branch. They'll merge together, but not before 10 and 27 will have been found to be similar and merge into a cluster as well. So you're building this all the way up, and you end up with, well, one cluster here at the very top. The user for this example has decided to cut the clusters once they've reached a dissimilarity level of 0.6. And doing so has basically chopped the dendrogram into 5 components. You have this yellow cluster, this violet cluster, this blue cluster, this green cluster, and this standalone cluster here in orange. And the idea here now is that if you look at these, you should be able to recognize things that they have in common. Like if you were to say, try to describe the observations in the violet cluster here, how would you describe them? Well, you might describe them as being observations that have a very small total for the 3 components. Right? We're talking about, talking about small totals in general, and it looks as though yellow, the yellow component dominates. That's the way I would describe this. It's not enough to say that they have small values, because look here, observation 40 is small, observation 20 is small, and they're in different clusters according to this. But there is, you know, like some variation. Some of them have no violet, some of them have a little bit of violet. There's some variation. If you look at observations that are in the green cluster, they all seem to have a pretty similar orange quantity. Observation 20 is a little different. It seems to be a bit of an oddball in this one, but still, you know, it's considered to be similar perhaps to 10 and 24 in a sense. And yeah, so orange seems to be constant throughout. That seems to be perhaps the best description for for the green one. For the blue cluster, you would say, oh, large values of yellow, roughly speaking, constant throughout. And the orange values are a bit smaller on average, but again, seem to be fairly constant throughout. And then violet is all over the place. And then for the yellow cluster, well, that's a little bit harder to describe. I'm not sure that I can come up with an easy label for it. And then finally, you have observation 5, which actually does look fairly different from everything else. Typically, when orange is large, like very large, you also have large violets or pinks here, and this isn't the case here. So this one is different. It's in its own cluster. But you see the thing here, it's actually difficult to come up with a good description of the observations in the cluster. It's hard to come up with a label, and you will encounter the same issue. You're going to have corporations that have certain things that look like they're common or similar to all the observations in your cluster, but that's not going to be a be-all and end-all. It's not going to be a description that matches everything that's in your cluster, and nothing that is not in your cluster matches it as well. And that's always a problem with clustering. So we're giving it like a sort of an average-ish, almost like stereotypical description of the cluster. You could have cut at different levels. You could have decided to cut when the dissimilarity was closer to 0.4, say, in which case you would have ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 clusters if you'd use a dissimilarity of 0.4. So you see, you do have a choice. Except it's a choice which is made based on the understanding of dissimilarity, or similarity if you build it this way. It's not an arbitrary choice like saying, find 7 clusters. It's going to be, find me clusters which are the optimal clusters, assuming a certain threshold level of dissimilarity between my observations, right? So there's some subject matter expertise that can come into play here to decide where you cut the clusters. So there's a data set, and this is one of the notebook examples that I'm going to show you. I'm flat out going to tell you before we start that I didn't scale this data set. I wanted to show you what would happen if this wasn't done with a scaled data set. Afterwards, I believe in my notebook I have the example where we do the same thing with the scaled data set. The data sets don't have to be scaled so much as the difference between the measurements have to be similar, right? And then here we have a bunch of variables. Look at mileage, and you look at displacement. The displacement seems to go from 71 to, what's the biggest value here? 460. This is a pretty big jump. And mileage per gallon goes from 10 to 33. It's a big jump, but not nearly as big of a jump, right? But in a sense, you can sort of view those as being big jumps together. Like on average, if you look at the distances for the displacement, that doesn't seem to be that much of a distance. Same thing with horsepower. Like, yeah, the range is huge, but on average, the pairwise distances might be somewhat on the same page, and that's, at least as a first pass, not the worst thing that you could do. At any rate, let's say that this is the dendrogram that comes out of this. Then you would say, what are your observations that are closest together? And it certainly looks as though these two vehicles here, the Mercury 450 SE and the Mercury 450 SL, are considered to be the closest vehicles, the ones that are most similar. Is that surprising? Well, no, because they basically have not only the same measurements, it's the same car, just with a slightly different set of options. It's not surprising that they would actually be found to be the closest or the most similar cars. Even though we didn't scale the data set, the type of stuff that you would expect to see happening is what actually happens, is what comes out here. Does that make sense? Okay. And if you take off your glasses, take a few steps back and squint at this, I'm seeing 3 clusters, I think, is about as many clusters as I'm able to see in there. That's what seemed to emerge as my natural grouping. 3 or 4, depending on where I'm where I decide to cut the line. Now I have here the same data set, again unscaled, but this is not about the scaling issue here. It's about showing you what happens if you pick a different set of parameters. If we use different distance metrics or dissimilarity metrics, or if we use different linkage strategy, how we merge clusters, we get dendrograms that sort of look different. They look different, but are they very different? Look, in all of them, Merck 450 SE and the Merck 450 SL are pretty close to one another, and also very close to Merck 450 SLC. Like I have the same issue here, right? Where's my Mercs? Merck 450, it's pretty close to one another. Where are they? They're here, they're here. So even though it looks like this topology is different, well, there's some groupings that are consistent. That's the kind of stuff that you're interested in as well, because this is saying that the existence of this cluster is robust. At least this combination of 3 is robust. It isn't specific to the choice of metric or the linkage strategy. In other instances as well, like you look at the Maserati-Bora, it always seems to be a bit of a standalone vehicle. Like when we don't scale the data, the Maserati-Bora always seems or always feels like it's different from all the other ones. Well, that gives us information as well. This might be an outlier. This might be something which is anomalous. It is always, roughly speaking, living in its own cluster on its own. Anything else? Well, certainly the trees look very different from one another, but I mean, if you look at the tree in the bottom left and the tree in the bottom right, they're not actually that different. And they don't have the same structure, but they have a lot in common as well, topologically speaking. How do you evaluate the results? I'm going to introduce here one metric that is used to determine if you have a good clustering scheme for your data set. So we've created a dendrogram, and again, like I'm reiterating the fact that in the real world you would need to scale your data before you do any of this. But let's pretend that we trust the dendrogram that we found, and we're going to decide to cut it at a height of about 250 right here. So we shake it off and we get 4 groups, 4 clusters. So we can measure something called the silhouette metric of every observation. So I have my 32 observations, my 32 vehicles are here, and for each of them in a cluster I compute a silhouette value, a silhouette metric. And what we're seeing is that, sorry, I went too far. What we're seeing here is that amongst the observations in the first cluster, which contained observations 10, 11, 6, 2, 1, 4, and 30, most of the silhouette values are, above 0.4. There's a smaller one here at about 0.25. And you look at the second cluster, the one with most observations, same sort of idea. I have a lot of very strong silhouette metrics, very positive values, and only a few small positive values. Same thing with my small cluster with only 4 observations. But there's a cluster here with 10 observations. Most of them are pretty much where they should be. One of the silhouette values, however, for observation 17 is negative. It is not where you would expect it to be, right? So this one here, this negative value, and I'll explain to you how you compute the silhouette metric later, but this is basically saying this one is not in the right cluster. It's not where you would expect to see it. So we're looking here for the cluster with 10 observations. Which one is that one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's not this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it is this cluster here. And in this cluster, there's one observation that feels like it shouldn't be there. It should be somewhere else. It's not easy to tell which one it might be just by looking at it. I suspect it's probably the Chrysler Imperial, but I don't know that for a fact based on this. Okay, so this tells you, roughly speaking, if your clustering scheme assigns observations to the right clusters according to the silhouette metric. How is it being measured? Well, it's a metric that takes into account the fact that in general you would like the average distance to point in its own cluster, in your own cluster, to be low. And you want the distance to points in the other clusters to be high, because you want the clusters to be isolated as much as possible. So you compute the silhouette metric by looking at the average dissimilarity of a point with its neighboring clusters, all the other clusters, and you subtract from that the average dissimilarity within your own cluster. So you would want the dissimilarity to be high with the other clusters, and you would want the average dissimilarity in your own cluster to be low. So generally speaking, the numerator should be high, should be a large value, and then you'll take the maximum, or you'll divide that, you'll scale that by the maximum dissimilarity value of that observation, either within its own cluster or outside of the cluster. So you'll get a positive value here if the average dissimilarity with the neighboring clusters is larger than the average dissimilarity within your own cluster, which is what you want. And you'll get a negative value if there's a lot of dissimilarity within its own clusters, and it looks as though there would be a fair number of observations in other clusters which you would be more similar to, have lower dissimilarity. So this is what the silhouette metric actually does, and out of this, what we're guessing here is that one of these is probably misassigned. It could be that it's an outlier. You can think of it as an outlier, but you can also mostly think of it as saying, I might need 5 clusters instead of 4 clusters. Perhaps this is what I need to do instead, right? Because if you bring it down to 5 clusters, now you'll have this cluster here being the same, this one being the same, this one being the same, but this one here will be broken down into 2 clusters, a cluster with 3 observations and a cluster with 7 observations, and perhaps you will find that these observations are in fact well clustered together. So another way in which you can decide at what height you cut the tree is to compute the silhouette metric, or see the silhouette metric for all of your observations as you change the height, and then you might decide to cut the tree whenever all of the silhouette metrics are positive and above a certain threshold, certain value. That could give you some information there. And you can also get a sense for the average, or how well the clustering scheme works as a whole, by averaging the silhouette measurements for all of the observations. And here we have a 0.38. That's a pretty strong value if you average all of these numbers here, including the negative number, which would suggest that, well, that could be how you decide which clustering scheme you pick. You try to maximize the silhouette metric. Now, one of the issues with clustering and unsupervised learning in general is that you've done it this way, great. Somebody comes along and decides to use a different measurement of validity, not the silhouette metric, but perhaps the Davies-Bouldin index or the Dunn's index, and the results aren't necessarily compatible. You don't have a formal definition of what clustering is, or what a good clustering scheme is. And so you can optimize an algorithm for a specific internal validation metric, and if you're lucky, and it turns out that when you optimize for if you're lucky and it turns out that when you optimize for different metrics, you get the same clusters, well, this is indication that these are probably the true clusters. But more often than not, what happens is you try to optimize for a different metric and you'll get completely different clusters. which means that there might be some structure which is constant, like it looks as though the mercury cars will always be together, and it looks as though the Maserati Bora will always be slightly different in its own cluster, but the rest might be like changing completely from one algorithm to another, or depending on what you're optimizing. So again, you never just build one clustering outcome. You build multiple outcomes and you look for the things that stay constant. I feel that this is not something which is actually explicitly stated very often in the literature. Like if you do your own researches online and see what other people say, perhaps I'm over-exaggerating the importance here, but I rarely see this being like pushed forward as an important strategy, right? You never, ever, ever satisfy yourself with the results of one run, one algorithm. You run a bunch of them, and then afterwards you look at the results, the clustering schemes, and you see how often observations stay together. I'm going to describe a little something like this when we do clustering validation, which is basically, I guess you could call it a clustering ensemble, which is to say find ways to combine the results of multiple runs, not unlike the ensemble methods we saw for anomaly detection. About the only author About the only author which I've seen discuss this to some extent is Charu Agarwal. This isn't this is one of them for outlier analysis, but he does have a book called Outlier Ensembles, and in there he does talk about the importance of ensembles, not just for outliers, but it's in the references in the original notes. There's not as many people as you would expect that sort of mention how important this is. So yes, that'd be my one thing to keep in mind that I would like to tell people about. Okay, so let me just give you a small demonstration of how you build the tree from the bottom up with this data set. Again, a reminder that it's not scaled here, but let's pretend that this doesn't matter. You look at all your observations, you find out which ones are closest together, and then you will group them together. Again, in this specific version of the algorithm, we're using a complete linkage strategy. It is these two cars which are found to be closest to one another. Right, it's not the same data set as the one we had before. We don't have the Mercury 450 SL or SC. These two get merged together. Then the next one up, actually we do have the 450 SE and SL. There we go. they're right there. My apologies. So they get merged together. And then the next one could be this one. They get merged together. Next one up in the height. Now it turns out that the thing that had two observations was deemed to be closest to that other observation. They get merged together. And then if I did a little jump here, you're getting a bunch of these clusters, and eventually clusters merge again, and you might get only two clusters here, and eventually just one cluster. So the distance metric that you've picked, though, might change the topology. The linkage strategy might change the topology as well. Look here at the same data set, clustered using two different distance metrics, Euclidean and Manhattan. They look different. Certainly the height is different because you're not computing distance the same way. The distance values will change. That's for sure. So the height goes from 0 to 600, and here we have 0 to 400. So these are different heights for sure. But how different is the structure really? I mean, there's two clusters if you use the Euclidean split, really. Like there's the branch on the left and the branch on the right. And here I get two clusters as well, branch on the left and on the right. Just out of curiosity, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright, so I have a little bit more than 14 observations. So these are different clustering schemes, but how different are they really? Do I really have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so yeah, truly they are. How different are they really though? And then you have to go down and look and see what's in common and what's not in common. And let me re-emphasize again, because that's a pretty important thing to see. Here, all the 3 mercuries are meant to be found to be close together. And if you go to the other one, the mercuries are still found to be close together. And the Maserati-Bora here is standalone. So is it here. So things keep on repeating, or certain things keep on repeating depending, no matter what distance metric you pick. That is information that you would literally keep in your notebook of important insights about this data set. I'll talk a little bit here about what we mean when we talk about similarity and dissimilarity. Look, we have these observations and they have features. So for each observation we have a signature, a profile, according to the measurements. So we can decide to compare objects, like one car with another car, or we can compare specific values, for one car for one variable, for another car for the same variable, or we could compare groups of cars, see if the groups are alike. But you can also compare variables. Say, how does the MPG variable as a whole compare to the displacement variable as a whole? This is also something you can do. So we can compare on the observations, we can compare on the rows, but we can also compare on the measurements of the observations, on the distributions of measurements within the observation. And that's something to keep in mind as well. This is roughly speaking the equivalent of transposing the data frame in which the observation is found, and now you do clustering on the columns rather than doing clustering on the rows. And this is also something that could prove to be useful, finding which variables are alike and which variables are different. Because if 2 variables are alike, you might not need both variables in your data set to start with, and that will allow you then to reduce the number of variables of interest, which would mitigate some of the effects of recursive dimensionality. So we will talk about linkage here quickly. How do we combine these clusters together? You could decide that the distance between 2 groups of observation is going to be the smallest distance between one observation of a group and an observation of another group. Now, it makes sense. If that distance is small, then there's a good likelihood that you might have something like overlap between the groups. And if the smallest distance is quite large, then you have separation, clear-cut separation of the groups. You could also pick the largest distance between observations. If you pick the largest distance to measure the distance between clusters, what you're saying is that if that largest distance is small, again, there's a good chance that there's overlap. And if the largest distance is large, you're less likely to have overlap. But if the largest distance is large, that doesn't mean that the clusters will not necessarily overlap. Right? We're talking about likelihoods here. You could decide to do all of the distances from observations in one cluster and the other. You look at all of them, and you do the average of these distances. Or, instead of averaging over the distances, you could average over the points, create the centroid, average over the points in the other cluster, also a centroid, and then compute the distance between the centroids. And the algorithm that you pick here for linkage, that's going to affect the shape of the clusters that you get. You might get clusters that are tighter or clusters that are looser based on the linkage that you've selected. I didn't give you an illustration here, but there's another linkage strategy called Wald's linkage, W-A-L-D. That is probably the best choice of linkage given if you know nothing else about the data as a whole. Single linkage. If you use the smallest distance, typically speaking, they're going to be better to deal with shapes that aren't blobbish. If you have shapes that are, like strings or chains, smallest distance will be able to find these clusters, or at least it's better suited to find these clusters. But it is quite sensitive to noise and outliers. And it does have a tendency to produce these cigar-type shaped clusters when you plot the data. Complete linkage, if you use the largest distance to determine the distance between clusters, then you'll get balanced clusters, which are typically going to be of the same size. They're not that sensitive to noise, but they tend to split large clusters into like I said, equal-sized subclusters. Same size, same shape, same diameter, or at least similar diameters. That could be interesting or important to you. If you're looking for outliers, though, this isn't great. If you're looking for outliers, you want stuff which is sensitive to noise and outliers, because if you remove the outlier and you get a completely different set of clusters, or remove the suspected outlier, then there's a good chance that you've identified an outlier. That's one way for you to find things that are not like the others. Average linkage, that's a compromise if you want between single and complete linkages. If you look at the average distances, not too sensitive to noise and outliers. It does tend to produce clusters that are blobbish, so of equal size in every direction, roughly speaking. That might be something you're interested in as well. And the centroid linkage, well, the problem there is that clusters can have a lot of internal variance, and when you reduce the cluster to a centroid, you're basically saying, forget about the variance. I'm just looking at the average value of the observations. I'm just looking at one representative, and then you've lost the ability to incorporate the variance that, one cluster can have a lot of variance, another one can have very little variance, and you don't have access to that anymore. You've lost this bit. Okay, anything else? I'll skip over that. This isn't important for us here. If we were trying to determine if we have, which of these 4 clustering results was the best. So here we use the Euclidean distance in 3 cases. I use a single linkage, complete linkage, average linkage here, and for the other one I use single linkage but with the Manhattan distance, and I get the following silhouette profiles. It definitely looks as though this one isn't great, right? We have a lot of negative silhouette counts, so we'd probably eliminate this one as a likely choice. And we're always trying to pick out 4 clusters, and this one has a few negative values, but it has an average silhouette width of 53, which is good, much better than the 0.4 that we had here. These 2 are exactly the same, turns out. If you use the average and the complete in this example, the silhouette metrics will be the same. That happens. It's not something that is impossible. You'd probably pick one of these 2 here as perhaps being a better fit or a better suit. On the other hand, we see a lot of very large values here. Perhaps what this is really telling us is that there is more than 4 clusters. But there's, in fact, we should be looking for a different number of clusters, and that might be the best approach here, the Manhattan distance, using single linkage, but using a different number of clusters. All right. It is deterministic, so once you've picked a distance metric, a similarity metric, and a linkage strategy, the tree that you build, the dendrogram, is always the same. That doesn't change. So that's a bonus because you only have to run it once. You never have to run it more than once. But, with few exceptions, it is very prohibitive when the time comes to run it. If you have a large number of observations in your data set, this is probably not a good choice. There are methods to speed up the process using parallel programming, but then you need to have a framework and an infrastructure in place to be able to do large size hierarchical or big data hierarchical clustering. You should check out Wald's method as a different way to link clusters. That's good. So a few notes here. Easy to understand, easy to implement. R has a specific function called hclust, which will automatically compute it. It's quite simple. But you need to choose a distance metric in your linkage criteria, and there isn't really a strong theoretical reason to pick anything. I mean, yeah, the metric is, you have to pick a metric no matter what, but you know, which linkage criteria you pick, it's completely arbitrary. We don't like these things when they're completely arbitrary, right? It feels like that's perhaps cheating a little bit. Of course, one solution is to try all the possibilities. Then you don't have to make a decision about which one is the best one. What you'd care about is looking at how often observations are found in the same cluster. Now you can remove the arbitrariness of making a decision at the cost of expanding the number of clustering schemes that you will find or compute. Hierarchical clustering cannot deal with missing values or mixed data type, unfortunately. I mean, unless you hand code how things work, unless you hand code a data function, a distance function that allows you to deal with these things. And that's something that can be done fairly easily. But it's at least when the way it's implemented in R, you have to have everything of the same type of data. And missing values, if you have a missing value, either you get rid of that variable for all the observations, or you get rid of that observation, or you replace the missing value by some well-guessed replacement value. In general, as I said, perhaps a better approach would be to use something called latent class analysis. I am not going to talk about this, but I did want to talk about hierarchical clustering because it allowed me to talk about the idea that you produce multiple runs using different methods, and that to introduce one of the methods, metrics to decide if you have a good clustering scheme or not, the silhouette metric.